G'day, Chris here and welcome back to ClickSpring. So there are two main components to the job of making our own spur gear cutters: generating the cutter profile and creating a suitable amount of relief behind each cutter face. So let's look at the profile first. There are two dominant classes of gear standards in common use today. One is based on the involute curve and the other on the cycloidal curve, each of which, if strictly adhered to, are not particularly straightforward to form in the home shop. But if we take a step back and look at the big picture, we can make a few broad statements. Firstly, that gear teeth are formed by removing the metal between each tooth. So what we'd like to make is in fact the profile defined by the gap between each of the teeth. Secondly, if we take a close look at that gap and exclude fillets from the discussion for the moment, we can break it down into some fairly straightforward elements of curves and straight lines. If we can mathematically define each of those elements in a simple way, then we've got everything that we need to generate the profile of our cutters. And this is where we get our first break. If we look at the text of the cycloidal standard, we see that our curves are in fact not cycloids at all, but rather just simple radii. When the standard was drafted, it was recognised that a radius was not only a good approximation for the cycloidal curve, but that it would also enable much easier manufacturing processes. The rest of the geometry is defined in the standard, using straight lines or otherwise practical elements. So right away we know that we can make this profile, because we can certainly generate an accurate radius in the home shop. Now we need to know the dimensions and how to bring it all together, but they're just numbers, all defined in the standard and presented in this calculator. Okay, so what about the involute profile? Well, things aren't quite so accommodating in this regard. There's no convenient radii written directly into the standard. But what if we applied the radius approximation anyway? It's not a huge deviation from the involute profile at any given tooth count. And it compares favourably to the error that we already accept from a set of commercial cutters at the end of each cutter range. So again, providing we're happy to accept this small compromise, we see the involute profile can also be simplified with radii. And so generating this profile also falls within the capabilities of the home shop. Now what we've just covered is the basic engineering premise that underpins a range of button cutter methods that have been serving clockmakers and model engineers for decades, each with their own set of compromises depending on which route is taken from here regarding solving the form relief problem. We're most interested in a straightforward solution that'll still give professional results. And one method that fits the bill well is an arbor that carries the cutter blanks eccentrically. It permits a very straightforward profile relief to be generated on a multi-tooth blank as 4 distinct lobes, and then a section of each lobe is milled away to reveal the cutter faces. So that's the basic idea. Let's kick things off with an example. For our first gear, we're going to cut a 0.8 module 30-tooth involute gear with a 20-degree pressure angle and a clearance of 0.25. Once the data has been put in, the calculator generates all of the numbers that we need to form the button cutters, the gear cutters, and also the gear blanks. And we'll come back to each of these numbers in turn as we need them throughout the process. But right now, what we need first is this number here, the diameter of the button cutters. This figure corresponds to the nominal diameter on the button cutter drawing. However, as with all of the nominal dimensions, the actual figure to use comes directly from the calculator. Now the sharpening tool from the previous episode is a light-duty hand tool, made from relatively soft materials like brass and mild steel. Our cutters, however, are going to have a much harder life, and so need to be made from a much tougher material. And there are several heat-treatable steels that could fit the bill. But O1 tool steel tends to be the go-to candidate for this sort of job in the home shop. Like most of the high-carbon steels, it's relatively easy to work in the annealed state, so we can form the delicate shapes that we need using common home shop tools. But its big plus is that it's so easy to heat treat using the standard home shop method. No special gear is required, just a propane torch and a bucket of oil. Now you'll recall that I mentioned that this little cutter carrier serves multiple roles, and here's what I mean. The small holes behind the main slot are designed to carry the button cutters, both for the formation of their rake angle and also for sharpening. The design calls for a set of 4 grub screws to thread into the various holes to make all of this work. And just as a quick aside, I've rounded off the ends of the grub screws to minimise their capacity to bruise the button cutter shanks while they're still in their annealed state. Just a quick touch on an abrasive belt or stone and they're done. One pair of the screws goes in at the sides and so acts to lock the button cutters from moving when inserted in the carrier. The other pair of screws insert into the underside threaded holes and perform the role of a simple jack. They can be screwed in to a high degree of accuracy to advance the button cutter faces to a specific height relative to the tool. Once in the correct position, the side screws lock them off. The buttons are designed to insert in the unthreaded openings, and for this next machining step, we'd like them seated dead flat on the carrier for maximum rigidity. Once in position, they're locked off with a side grub screw. So what we have here is an excellent little fixture to hold the button cutters while we mill a rake angle on their top surface. Now, as it happens, with all of these holes in close proximity, there's an opportunity to use the various shafts, pins and screws as a crude sine bar to conveniently set the correct angle for the fixture in the mill. Just drop the fixture into place like this and then close the vise. Once the fixture is being held by the vise jaws, the grub screws can be tightened down on the button cutters. Now of course, it's not overly precise, but it doesn't need to be. It makes setting the angle convenient. And it'll certainly give us an angle close enough to the 15 degrees that we'd like to see. That's one way to set up the work, and here's an alternative. Again, the guide shaft and this time the indexing pin form a good approximation of a 15-degree angle. And that's our raw button cutters formed. So the next step is to harden them, using the usual home shop heat treating process. First, bring the part to the correct colour, preferably immersed in something like powdered boric acid to minimise the oxidation scale, and then quench. I tend to use a generic compressor oil for quenching O1 with good results. The glaze from the boric acid can be removed with boiling water, and then it's on to tempering. This is the same setup you've seen for bluing screws, except this time I'm stopping well short of blue. In fact, I'm barely letting any colour develop at all, aiming for the shade generally referred to as pale straw. It corresponds to a temperature of around 230 degrees Celsius, and it'll give a hard cutting edge with a small amount of toughness. And you can see it's not that much of a colour change at all, just the barest change to yellow. A small trade-off has been made within the structure of the metal, with the glass-hard martensitic structure being slightly transformed into something a little tougher. Exactly where to set that trade-off is usually something that comes from seeing what works. If, for example, the tool were to chip in use, then it's worth taking the temper colour through to something like a medium or even a dark straw if needed, sacrificing a little of that hardness for more toughness and so ensuring a better retention of the cutting edge. And this brings us to the other use of the sharpening tool, which is to sharpen the button cutters. They're inserted into the carrier and then aligned so that the plane of the rake angle tilts back like this. And depending on how the parts have been held in the mill, the tool marks can be of use in getting this alignment as close as possible. The lower grub screws are then inserted and the buttons are advanced so that each sits the same amount forward of the carrier face. Now how far forward the buttons need to sit from the face of the carrier becomes clear once we reassemble the tool and have a closer look at another of the features built into it. The throat dimension of the locating plate has been set to again give an approximation of a 15-degree angle. This acts as a natural stop, so of course to bring the buttons into contact with the stone and give us some material to remove, they need to sit slightly beyond that limit. With equal adjustments to the jack screws, each button can be advanced until both are sitting just barely forward of the plate. Whatever it takes to move one button forward, then the other can be adjusted in exactly the same way, by applying the same number of turns to the screw. A visual inspection is enough to get it fairly close. And of course, it's easy enough to cross-check it and confirm all is as it should be using calipers. Once both buttons are set correctly, just the barest hint of daylight remains between the carrier and the locating plate. Again, it's roughly 15 degrees when the carrier contacts the locating plate. So of course it's currently sitting slightly above that and will be slowly reducing towards it as I grind down the faces of the cutters. The tool has a natural tendency to form a vacuum lock with the surface of the stones, so not a whole lot of downforce is required to keep it all sitting flat on the stone during the sharpen. Now the finish directly off the fine stone is certainly good enough for what we need in a cutting tool, but I thought it might be interesting to see how it performs on a tin lap with diamantine powder. And it turns out it's a good platform for going all of the way through to a black polish. So I think it's fair to say that without much modification at all, this sharpening tool could also become a decent screwhead polishing tool, if for example you need it to have an additional purpose to justify the effort of construction. In any event, with that the button cutters are complete and can be released from the carrier. Next up is what I'm calling the button cutter shank, essentially a platform to hold the buttons at the correct distance apart and at the correct angle to form our gear cutter profile. Again, a key dimension of the tool is nominal, the button centre distance, and its value is to be taken directly from the calculator. But another important dimension is the slope of the small platform on the end of the shank, upon which the button cutters will rest. We'll be using 5 degrees, so this means that the buttons will be tilted forward by 5 degrees when the shank is mounted horizontally in the tool post on the lathe, giving a maximum of 5 degrees clearance at the front of each button. And keep in mind that depending on your lathe centre height, there may be an issue in getting the button cutters low enough in the tool holders, so you may find that you need to mill the platform a little deeper to make it all work. As it happens, my lathe centre height is such that I can get away with just taking a small cut off the top, before dropping in the holes for the button cutters. A small V-groove takes care of the clearance requirements directly beneath the button cutters. And a quick touch on the belt sander ensures that the rest of the front of the shank is also clear during the cut of the gear profile. Again, I'm being careful to maintain that 5-degree angle throughout the sanding. The button cutters are then manually positioned on the shank, ensuring a 45-degree rotation of the high point of each button towards the centre line to make the most of both the rake and the clearance angles during the cut. And although it might look difficult to ensure correct positioning, in practice it's fairly straightforward. Okay, so with the button cutter assembly complete, we can now take a look at what I'm calling the cutter arbor. Its main role is to eccentrically carry the blanks for cutting on the lathe. Now, despite its primary role being that of carrying multi-tooth blanks, much like the sharpening tool, the arbor has been designed to serve more than one purpose. For example, you'll notice that it has a small channel sunk into its face. This allows us to use the tool to also produce simple fly cutters, using the exact same button tools and calculator that we're using to form the multi-tooth cutters. It's also a fixture to hold onto the multi-tooth cutters for the milling operation that reveals each cutter tooth. This large flat serves to both balance the tool and give us clean access to the section that we'd like to mill away. And then by removing a small section at the back, we get a means of both aligning and gripping the whole structure in the vise, as you'll see in the next video. The last component to be made is the small mild steel insert that forms the locating boss for the multi-tooth blanks. And that's the tools complete. In the next video, we'll put them to use making some cutters. Thanks for watching. I'll see you later.